So you will get a skeleton for the practical test. Since the practical test is about compression, you will get a method which is empty, which says write your own compression code, and then a method which is empty, which says write your own decompression code. Right? And then there will be an input routine which is provided for you. But after you've done the input, you will have to write your own extra method that does some sort of conversion on that input. Okay, but it's rather obvious what you have to do. Okay, so the whole binary standard in thing will not have any effect on the scripts that mark the prep. Okay. But to come back to my comment of yesterday, in other words, you will get an input routine which you can just analogously write an output routine. But I would still advise you to, once you've read in with the provided input routine, that the very first thing you do is get those conversions right. Yes? Because you'll need to do, on the provided input, you'll need to do some conversions to actually start the compression. So get that right first. Okay? Get the conversions right from the input. Just so that we can have something to mark, of course. Okay? Right. This was just the chat before 9, but it's 1 minute past 9 now. So we can start. For what it's worth. Okay. Right, compression. Are there any questions about run length encoding? No? Mr. Wilmot?
Just a quick question about the practice. Will we be able to run test cases ourselves?
Yes. Yeah. And as with the previous practice, you actually get the test cases that you have to get working, and it will so that it can be marked before you leave the room. Yes. Now, I think there are only 5 test cases. You will not have to sort of sit there and look at the zeros and ones. If you do the input and generate the output, it will be absolutely obvious immediately whether you got it right or not. Because it can take ages to, sit there and you miss 1 0 or 1 1 or something. So it will be fairly obvious whether it's correct or not. Yes.
Gaan nou 'n bitmap vraag wees vir online encoding?
Nee, ek kan nie dit antwoord nie. Want jy weet, sê ek ja, dan gee ek vir jou die toets, sê ek nee, dan gee ek ook vir jou die toets. Okay. So, ja. Yes. Any more questions? Happy? Okay. There is one more thing. Please send me an email to remind me to send it out to the class. For project 3, if you do not attach a plagiarism detection at the back of your report, I will not mark the report. That understood. If you do not give me a hard copy of the report, you have to have that report on Git so that I can get it. Yes? Including the plagiarism detection. I do not mark documents that are not in PDF format or not using the double negative. I only mark reports in PDF format. Okay? I don't mark Word or PowerPoint or Excel or ODS or whatever you have, right? PDF. I do PDF. That and only that. Okay? I actually had 2 people in project 2 got zeros because they didn't hand in PDF projects, at least 2. So, don't. I felt like an idiot afterwards and gave them marks anyway, but not as many as they should have gotten. Ja, meneer Eis, jy smaal want jy was een van die ODS-kandidate. Okay. I don't do that. Please don't do that. PDF only. No plagiarism, no marks. No plagiarism form, no marks. Right? I will have a list where I will have to be present. And you have to sign that list to state that you handed in your report. Yes, because there were about 5 people who said, oh, but I handed in the report, but I never got the report. And so it's a mess if you just hand it in class. Okay, right? So next week, Wednesday, I'll be here with my list. And you have to physically give me your report and sign the list that you've handed in your report. Okay? So that we can sort out this, oh, but I did push my report through your door. Which means that if you want to hand in a hard copy, it has to be next week, Wednesday at 12, during the lecture time. Okay? If you don't hand in your report at 12 next Wednesday, you have to have it on Git. Otherwise, how do I get it? Yes? And it has to be on Git by the hand-in time for the project. Okay, so you actually get more time if you leave it on. If you hand it in via Git, 3 or 4 hours. Okay? Yes? Is that clear? Okay. Timing for the rest of the course. Isn't that a spectacular thing to say? So today we do Huffman encoding. Monday we do the compression, Huffman compression. Monday we do Lempel-Ziff compression, LZW compression. Yes. Wednesday is a revision period. So if you have any other questions regarding the report, the project, the test that will take place on chapter 5, that is the time to ask, and that is then the last lecture. Since Thursday is traditionally your last, my schedule worked out that you would have written a test on Thursday, right? So I have no lecture for next Thursday because you would have gotten the lecture to study for the test, but then we moved the tests and now my schedule is a bit up in arms. So we won't have a lecture for the very last lecture of this course. Yay, 8 o'clock Thursday, right? Okay. Any question about logistics? Okay. Anybody who missed a test due and gave me a medical certificate, any assessment, and I got a medical certificate for that assessment, you have to let me know how you want to handle that, right? I think I got 2 answers on my email, and there were about 5 people involved, right? So you have to decide how you want to do it. You have to let me know. Okay, right. Can we do Huffman? Yes, let's run. Huffman looks at patterns, right? And the way it looks at a pattern, I forgot my laser pointer. Let me just get it on. Sorry. Point. Huffman says the following, very easy thing to do. It says, we are looking at specifically natural language files. I want to compress my, heaven forbid, MS Word file, yes, for some or other reason. Okay, any natural language files. In other words, you can also compress your Java files using Huffman. So it's a very general compression algorithm. And we know that in a text file, normally you need 8 bits per character. So Huffman says, well, can I use less bits per character? And the answer is yes. So instead of using 7 or 8 bits for each character, we use fewer bits for characters that appear often than those that appear rarely. So in abracadabra, exclamation mark, I have lots of A's, 1, 2, 3, 4, 5 A's, which is almost half the number of characters there appear is the A, right? Almost half the time. And then I have 2 B's and I have 2 R's and I have 1 C and 1 D and 1 exclamation mark. So the idea is I want to compress that A quite a bit. I want to apply the most compression to A, then slightly less compression to B and R, and then C, D and exclamation mark, I don't really need to compress very much because they appear only once. So it's not per se a pattern, but it is a pattern. The things that occur most often will be compressed the most. Which means that if you take any large natural language text file, your vowels will be compressed most. What is the character that appears most in English? Is an E. Yeah. You know that. Read up on cryptography. That's one of the ways you can use to break stupid cryptography algorithms. Did you do that at school? I doubt. Oh, you did. Okay, so you give every character in the alphabet a number. So 1 for A, 2 for B, or you can randomly have a key code that matches, not this, randomize the mapping. Yes, and then you write the numbers instead of the alphabet letters. Yeah? And then you'll find that you use E most often. But anyway, okay. 50 years ago, kids occupied themselves not with cell phones, but with things like that. Okay. So if we identify the character that is used most often, and we use only 1 bit for that character, and so on and so forth. That works very well, and here is an example. So I would have, for an A, I encode with a 0, and a B with a 1, and an R with a 0, 0, and a C with a 0, 1, and so on. But then there is, remember with run length encoding, I knew that I'm reading separate things. I'm reading the short ends, yes, in 8 bits. So I read 8 bits at a time. That gives me a number. I know that is the run, the length of the run. Over here, I have no idea how many bits I use for each character. Therefore, you have to have a delimiter in between. In this case, I used spaces. But that's silly, because then you have to store that space. Otherwise, you have no idea how many bits to read next. Am I looking at 0 space 1, or am I looking at 0, 1? You can't just put all the bits there. It's not readable. Okay? So that is not so cool. So somehow, if I have to store this space, the delimiter between the words, then it's going to waste a lot of space again. So my compression is not as good. So somehow, we have to get rid of that. And the way Huffman does it is it devises what is known as a prefix-free code. And this prefix-free code is uniquely decodable. Okay, so then if I use the Huffman code, then I'll be able to read this without any problem. Mr. Wall.
Just a quick question. They encode A with 0, B with 4 ones. Why wouldn't it be, why, I mean, is that 4 ones or 5 ones?
4. Aha. Hold that thought for a few seconds. And then you'll see the reason why we do this is to make sure that we make a prefix-free code.
Yes. Sorry, it's just minus 5 ones. That's why I was confused.
Oh, okay. Yeah. Okay. So what we want to do, the moment we read something, we start to read a bit. Remember, we read 8 bits or 32 bits, and then we go inside our Java code and have a look at each individual bit. So if I start with a 0, if I can make a code so that there is no code which is a prefix of any of the other codes. Now, what does this mean? Prefix is a voorvoegsel, the part in front, right? So if A is a 0, then none of my other codes can start with a 0. So that when I see a single 0, where I'm starting at the start, a single 0 at the start, I know it's just that one bit, it's the A. Okay? So then, for all the other codes, if I choose to encode A with 0, all the other codes at least have to start with a 1. And then, all these other codes, you'll see that they are quite a bit longer than this solution, but they are constructed so that none of them can be mistaken as the start of another code. For example, C is 110. This is not the start of this code, because this code is 1111, so the 0 is out of place. It cannot be this one, yes. It cannot be this one, and it cannot be that one. Okay, so there's none of these codes where I can move that code below another code and then it is the same as the first part of another code. Does that make sense? Okay, right. Okay. And if we can do that, then clearly this is uniquely decodable. Because if I get a 0, I know it must be A. Yes, so that's the end of my first character, the one and only thing there. Now I start with another character. Then I get 1, 1, 1. See, the 1, 1 is confusing because it can be either a B or a C or an R. So that, yes.
So you have an exclamation, then it goes 101, and then and then a C after that. So you have 101110.
Where are you?
Sorry about that. Still where
Here.
No, we defined it.
Yes.
So you've got the exclamation for 101, and then the C 110. So that gives you at the end 1110, which is the same as an R.
Yes, but you know where you start. If you put them next to each other, you know where you, if you put two characters next to each other, you know what the boundaries are where you have to start. Otherwise, of course, you can have a whole lot of confusion in between. But that's very important. You know where your code is starting. And if you know where your code is starting, it's unique. If you did not know that, yes, then this wouldn't have worked. Good observation. Yes. Okay. So how do I do this programmatically? How do I write the Java? And one of my favorite things in the world, we're going to use a try. Okay, you still remember a try from our string searches? What we're going to do is we're going to construct a try. And the try will work as usual. Remember, we have a binary code. So this is my key, A or B or C, my alphabet letters, and each of them need a code, right? So I wrote down the code. Well, the authors of the book wrote down the codes, and then they constructed the try corresponding to the code in the following way. I start at the root, then I go left with the 0 and I go right with the 1 because 0 is less than 1, right? Left on 0, right on 1. Then, if I go left on 0, every now and then, or right on 1, every now and then, I see that I have now gotten a code. So if I'm at the root, I get a 0. I have a leaf node with the correct character symbol in there. So 0 gives me an A. Look at a few of the others, exclamation mark, 1, 0, 1, which gives me a leaf node with the exclamation mark in it. Okay. But, of course, I still have to devise that prefix-free code, which is not a trivial exercise. And this is fairly easy to see. Here is another one. This is a prefix-free code. This is a prefix-free code. So there can be different prefix-free codes. So is one better than the other? How do I get there? Here I have only, 2, 4, 6 characters. So you can sort of do it manually by hand and test whether it's prefix-free. But clearly, if your alphabet is large, then this can become quite an issue, right? So, Huffman did exactly that. How do I construct that prefix-free code? Okay, and that is the crux of Huffman's algorithm. It's fairly easy to see. Let's put that on us for a moment. So what you have to do is you have given the code word table with the key and the value. I have to build the try. You all know how to insert into try, so that's not an issue. And then, this is important to note, you have to write the try into the compressed file, into your compressed output, because otherwise you have a code, yeah, and you compress something, and here's your compression, but how does the decompression algorithm know what the code is? So you actually dump the try so that you can use it in your expansion, which means that the try must be encoded efficiently. And then you can use the try to encode, and then when you want to expand, you read the try and decode. With LZW compression, the next one we're going to look at on Monday, there will be a slight difference with writing the try or not writing the try. Okay? Right. Also note that when you construct the trie, you actually have to store the characters in the leaves. Yes. So you have to know what those characters are. But the thing is, you write it in the trie once. So the size of the compressed file as each symbol that has to be used will be inside the compressed file once. And after that, I use the very shortened bit stream representing that character. Incidentally, you might want to think for a possible test question on the 20th of May. We tend to think of natural language files as having 26 times 2 plus a few other characters, punctuation symbols. And clearly that will work because my bit streams will be quite small, yes? Short. But what if I want to encode a Unicode file with Huffman compression? So my question to you is, will that still work or not? Because I've got a humongous alphabet. Yes, you remember that? Got a humongous alphabet. And so will it still be feasible to do compression if I have to store that humongous alphabet? Oh, yes. Can anybody see? Yes, thank you. Okay. Think about it. Okay, so the building the trie is fairly easy. I store my character. I say whether I go left or right, and I check whether I'm at the leaf node. Yes. But the one thing, if you look at, no, they don't have it in here. What we want, clearly, with Huffman compression is for each character, here's an example on the next page. For each character, we want to know what is the frequency that the character occurs in. Like in abracadabra, I had 5 A's and 2 B's and 2 R's. You have to know that in order to devise the code. So what we're going to do when we actually look at the Huffman compression, we have to be aware of what the frequency is, right? So in the trie, you'll see that I have a frequency there. But again, we now come to something which I think you haven't done often before. If you think about this very carefully, you have to read your input twice. So you have a 2-stage process. This occurs very naturally in computer science. We are used to, I read my input, I do my stuff, I give my output. Right? But with Huffman compression, you have to read the input and count. You have to get those frequencies. And once you've done that, you have to read the input again so that you can do the actual compression. You might want to ask Willem Bester next semester when he shows you the compiler, how you write the compiler. What about 2-stage compilers? You press him a little, let him think you read up on it. Normally compilers are 1-stage, but in the old days, before compiler theory was advanced, you had to read your input again and again and again for all the stages of the compilation. These days, we normally use a 1-stage compiler. And another thing which I'm doing with the honors class today, have you ever heard about bootstrapping? Yeah, You all know what bootstrapping is? Oh, okay. So I have a language. Take any, whatever language, CS214 language. And I want to write a compiler to compile that language, but I want to write it in the language CS214. That's a bootstrapping compiler, but anyway. I already gave you my standard warning on 244, have I? Yes, you're all aware of it. Pull up your socks. Be precise. Okay. Right. It's double the amount of work you have in 214, and it's double as hard. Okay? But Willem is an excellent lecturer, so. Right, okay. So we can easily see how we can compress. I read, with Huffman encoding, I read my input once, I count. How many times does each character occur? If you then give me a free, prefix-free code, I can construct the try. Yes, that's very easy. And I can compress. Given the try, I can compress. And it's easy to see how to do that. So the whole thing is, how do I construct the try? Now, this is somewhat of a bootstrapping process. I construct the try based on what I have in the try. So here goes. If you look at it in a diagram, it makes a bit more sense than the Java. So let's first look at the diagram. How do I construct the try? Well, what we do is we make a forest of trees. You're familiar with forests of trees? A tree normally has one root node. If I have a lot of trees together, it's a forest of trees. Yes. So I make, for every single character in my code, yes, I make a leaf node. Yes, so my root is also the leaf. And then I have a forest of these one node trees. Okay. And note that since these are the leaves, the symbol is associated with the node. So the char associated to the leaf node is there. And over here, just in the diagram, we wrote the frequency with which this character occurs at the top of the node, so that you can follow the picture, right? So there are 11 spaces. I don't know why they put the spaces in, silly, but anyway, okay. What are they doing anyway? There's a line feed, BRFHMAWOIEST, and 11 spaces. Oh, sorry, it's this example. Natural language text. Input, it was the best of times, it was the worst of times. So we encode, we want to compress this single sentence. So I have 11 spaces, I have a line feed at the end, and then you can count how many times. Lots of T's, lots of, no, 2 I's, 3 I's, 4. Let's see, did I count correctly? Oh, yippee, 4 I's. Okay, so that's a frequency with which a character occurs. And now we construct the try. And what we do is simply this. We take the first 2 trees in the forest that have the lowest frequency. So there's some order that the trees are in the forest. It's immaterial what the order is. Okay? So however you organize in your program, you take the first 2 with the lowest frequency. Okay? And you put them together in a new tree, right? So you combine them by adding an empty root node, because it's not a leaf now, so I don't have a character in there, and I add the 2 frequencies there. Okay? So now I have 1 less tree in my forest. Okay, meneer Uys, I have 1 less tree in my forest. Okay. Now I look at all my frequencies. I have a 1 and a 2 and a 2 and so on. And for some or other reason, I don't know why they decided to, but then they combined, can't really see because it's skewed. Oh, I had an R and this one, and now they combined the M and the A. Yes, doesn't matter, the order is immaterial. Combined M and A because they, okay, now I'm confused. I confused myself officially. Oh, sorry, no, I don't know what I'm talking about. I was mixing up two pictures. I do apologize. Let's start again. Take the first two with the lowest frequency, that's the L and the B, combine them, get a new tree. Yes? Then I take the frequency 1, 2, 2, 2, 2, 2. So 1 must be combined with a 2. Yes, because those are the two lowest frequencies. Yes, so I have to put R into this tree. And I do that. I combine the R with the frequency 1 and this existing tree with frequency 2, and I get this thing. I add the frequencies, yes, so this one is now frequency 3, and there's the R over there, and the L and the B. Okay? Yes? Note how the frequencies line the edges. Okay? R goes to the left of the new root because the frequency is less than frequency 2. Okay? Yes? Right. So now this tree goes there because it's frequency 3. Now I look at the next two with the lowest frequencies, which would be M and A. 2 plus 2 is 4, so I get a new tree there with 4. And so on and so forth. As easy as that. So look at how we always take the first two nodes. If this is ordered in frequency, if the trees in my forest are ordered based on the frequency, then I can always take the first two because they're the lowest. My word, and it just shouts, what data structure? Priority queue. Take the first two elements in the priority queue. Keep this thing in a priority queue, and I can always take the top two, the front two. Okay, and I combine, and you know that it's very easy to insert into a tree. We've done, or into a trie, sorry. And we keep on doing this. And if you keep on doing this, you end up with a complete trie where you have the frequencies for each node, yes, and it is nicely sorted in the trie so that a leaf node is at the bottom. Okay, that is a non-statement. With leaf nodes, with the characters in them at the bottom, and I've got a nicely ordered trie, and now I can do my Hoffman compression. Okay. Right. But the thing then becomes, how do I construct the prefix code? Because we've said how to build the trie, but I still haven't gotten a prefix code yet. But now, the nice thing is, if I look at my fully constructed trie over here, yeah, just remember the order there, that's EWO, blah, blah. So the very same picture over here. If I look at my trie, and this is too beautiful for words. If I look at my trie and I traverse my trie and I number each edge, left-leaning edge with a 0 and a right-leaning edge with a 1, I can read off my prefix-free code from the constructed trie. Isn't that too nice? Yeah. So you have to believe that for a moment. You can double check for yourself that this is a prefix-free code. For example, I've got an E, which is 000. None of the other codes. There's a 0011, but not a 000. There's also a 00. No 000s. Is anything starting with a 01? Remember that SP, which is the space, occurred most often. Yes, and look, it's got the shortest code. Right? Okay, I do 01 and I get to SP. This is so cool. Okay. Yes.
Do we still use those frequency values like before?
The frequency values we use to construct the trie. Are you asking whether it's still in the algorithm? Once you have this, you don't need them. You need the frequencies to construct the trie. So once you've constructed the trie based on the frequencies, you can build the prefix-free code, and then you're okay. So the thing is, we have to prove mathematically that this is a prefix-free code, because I'm just now saying it is. I might be wrong. Okay, so with Huffman, it's here. That must be the most horrible 2 words in this lecture room. Because that means you have, sorry about that, just occurred to me. It's almost as bad as I'm from America and I'm here to help you. Anyway, that means you have to learn a proof. It's got nothing to do with it. Okay? You'll have to learn a proof. Propositions T and U. In section 5.5, proposition T and proposition U, you have to know the propositions and you have to know the proofs. Okay? Right. We're just going to make it. And here is proposition T. For any prefix-free code, the length of the encoded bit string is equal to something called the weighted external path length of the corresponding trie. There's a big form. Okay? So let's just see, look at this for a moment. For any prefix-free code, so if I have a prefix-free code and I use that to construct a trie, yeah, then the length of the encoded bit string is equal to the weighted external path length of the corresponding trie. So let's have a look at that. Under optimality. Oops. I pointed out in the example that the character that occurred most often in the example, which was space, occurred almost at the top. Yes, SP was there. The 00 or 01? 01. Yes. Wrong picture. There we go. There's SP. It occurs most often. So this is SP is actually the leaf node nearest to the root. Yes, it occurs most often, and you can check for all the others. And it makes sense if you think how you construct the trie. I take the shortest, the smallest frequencies, combine them. Yes, and the smallest ones and combine them. So my leaf nodes will be very near my root. Okay? And if you look at the codes that occur, if I do the, oh, there we've got the names of the things in there anyway. SP occurs most often 11 times, so I'm just 2 edges away from my root. E occurs 5 times, so I'm 3 edges away from the root, and so on and so forth, right? And these things that occur only twice, or 1, 2, 3, 4, 5 edges away from the root. So the path length from the root to the character seems to indicate how often it occurs. And that makes sense if you think how we construct it from. So we define something which we call the weighted external path length of a tree. Okay. And the weighted external path length of a tree is the sum of the frequencies times the depth of all the leaves. Wait, what am I doing this? I'm doing maths again. You know that you can have different prefix-free codes, right? We had an example 2 pages back. So which one is better? Okay. And what we want to do is we want to define when is one prefix-free code better than the other. Okay. When will it be better than the other? It will be better if it uses less characters, less bits to compress the given input. Yeah? So if for one prefix-free code I compress to 21 bits, and there's another prefix-free code, and that compresses to 19 bits, then the one with the 19 bits is better. So I want to count the number of bits that are used to compress a given file. So over all the prefix-free codes, which one is the best? The one that uses the least bits is best. So how do we define that? We have a look and we say, this is a prefix-free code. Here is its associated trie. Let's associate a number to this trie. Yes. Or if you want to, then the same, it's because the prefix-free code and the trie is a one-to-one mapping, right? So I want to measure somehow the quality of this trie. And what we do is the following. We define something called the weighted external path length. So that is the sum of the frequency counts times the depth of all the letters. So think about it just in English, not in maths. In English, what I'm saying is, if my most frequently used character is encoded with 2 bits in code A, but 5 bits in code B, and then another letter here. So I want to compare the depth of that leaf and the number of bits I used to get there. Yeah, I multiply the depth, which is how many edges do I use to get there. In other words, how many bits do I use to encode that character. Okay, and then I do that for every single character and I add it all up. That makes sense? That is the weighted external path length of the tree. The sum of the weight, the sum of the frequency count times the depth of all the leaves. Yes? Okay. Yes, you're happy with that? Okay. And this is very easy to see then. If for any prefix-free code, the length of the encoded bit string is simply equal to the weighted external path length of its trie. Why would that be? Well, the depth of each leaf is the number of bits used to encode the character. Thus, the weighted external path length is the length of the encoded bit. Okay. That is just what I said in English, a bit more formal. Okay. And then proposition U, which is the last one. Again, I'm not going through the proof because you have to learn to read them by yourself. If you struggle with this proof, please ask me next Wednesday. Okay. What we have is that if you give me a set of R symbols and how frequently each of them occur in my input text, The Huffman algorithm builds an optimal free prefix code. So using the Huffman algorithm, I cannot get a better prefix-free code. Yes, where better has been defined. Okay. And the proof here, maybe I should go through it. No, I can't. It's a proof by induction. You all know how induction works. State the base case. Yes. So we'll assume that it is optimal for less than R symbols. And then we add one more symbol to get to R, and we show the optimality still holds. Okay? If you struggle with the details of this proof, please ask me next Wednesday. Okay? Great. So Monday is the last compression algorithm. Wednesday is revision and project report hand in. And that's it. You survived 214. Good luck. I'll see you tomorrow afternoon. Yeah. And again, for the practice, do it step by step. Don't have all these methods that sort of halfway get there. Start something you have to do, complete it, because the tests are incremental. They test this characteristic, that one, can you do this, can you do this, can you do this? Good. Thank you, I'll see you on Monday.